Alright, let me set the context for the video. This video is a high-level roadmap to learn CS in one of four niches: full stack, DevOps, AI, and Web3. These are the four niches where it's sort of easy to get an entry-level job and provide value to a company on day zero if you have gone through the syllabus well and if you have actually built projects that showcase that you're good at one of these four skills. CS generally is a fairly vast field, and you can go very deep into learning various concepts of CS, but these are the ones that require engineers and require basically human labor to be able to execute fast in a company, which is why these are good niches to pick in case you're looking for an immediate job in the next 3 months, 6 months, whatever that timeline is for you. Generally though, if you're just starting out, it'll probably take you 6 to 8 months to get decent at one of these niches. I would also suggest if you are just starting out, then probably just stick to full stack. But if you are if you've done a little bit of CS, you already have a job, you're in college, but you have a decent DSA, then you can probably pick up other things. If you're a complete beginner, probably just stick to full stack and go from there. With that, we'll dive right into it. We'll probably kick things off with full stack, which is the simplest one and probably fairly commoditized at this point. I think everyone knows what full stack is and has heard some level of the other of a jargon. I think merge stack is something that's fairly popular, slash very easy to target in probably 2 months if you have decent CSIQ. We'll kick things off with that. For full stack development, this is how I would learn it, and everything that's mentioned over here is, you can think of it like a cohort video, a 2-hour, 3-hour video that you have to go through. Some of these topics can be broken down into more than one videos, but generally I think most of these topics are a 3 to 4 hour follow along video or a grind, and then a bunch of projects slash assignments you can do on top of it. But generally kick things off with HTML, CSS. This is where people spend a little too much time, but I think one video or basically a week is more than enough to get on with the basics, then move on to JavaScript, because that's where you're going to spend most of your time anyways. Basics of JavaScript, that's just the syntax. The architecture of JS and async JS are two nice things to do early on, even though this is probably where you'll feel a little bit of a hunch if you are just a beginner. And if you haven't done any coding before, then maybe feel free to skip through these topics and come back to them later. Then comes the difference between client-side and server-side JavaScript, and why there is this difference, why was server-side JavaScript even introduced, and just understanding the various places you can run JavaScript. HTTP and Express, a more generic concept to learn, not just specific to the MERN stack, which is the one that we're talking about right now. HTTP is a protocol. We'll learn many protocols later on, but the most popular protocol that you're probably going to hit if you're using any application today, like a Zepto or a Paytm or a Blinkit, any website, 99% of the times you're probably hitting an HTTP server. So understanding this protocol makes a lot of sense, even though there are other protocols to learn. This is the one you'll probably spend most of your time building in team. One way to build an HTTP protocol in JavaScript is Express. So very popular framework. It's what E stands for in the MERN stack. And hence good for you to get really good at this, because you'll probably be interviewed in Express and what does one thing do or what does one function do in Express. So basically try to get as hands-on as possible on Express and spend a decent chunk of time here. So this is probably, probably 5 classes. If you're spending 3 days on HTML, CSS, then probably spend 15 days on Express. Then move on to databases and start with MongoDB. It's the simplest one. Very easy to digest. There's a reason most people choose MongoDB when they're just starting out. Because it hides a lot of complexity from you. You don't have the complexity of learning a new language like SQL. It sort of makes sense to follow this as a beginner. But eventually, definitely move to something like Postgres or MySQL, because most probably a company that you're joining is going to be using a SQL database, something like Postgres or SQL. And hence, once you're done with the basics, you've built a few full stack projects at this point, move on to learning Postgres really quickly, probably understand SQL, how to write SQL queries, and then eventually learn about ORMs and Prisma and Drizzle, other 2 ones, or the popular ones in Node.js. Just pick one of them, finish it off, and then that's your full stack. Not your full stack, that's your backend stack for the day. This backend stack can probably build everything that you need. A lot of big companies, small companies that you see are probably written in this stack, and if up until this point, you can probably understand most of their code bases and start to provide value to them. Iske baad, I think a lot of topics are important, probably needed. So I wouldn't just stop here. TypeScript and Bun.js are 2 topics I would spend a little bit of time on. TypeScript a lot of time on, but Bun basically just understanding how is it different from JavaScript or Node.js, and why is it being adopted a little more over Node now. Turbo repo is sort of the benchmark of creating monorepos, or not even monorepos, like whatever, a build system in JavaScript today. So whenever you open a repo for the first time, if you're joining a company or otherwise, you'll probably be hit with a bunch of turbo repo jargon. So it makes sense to just, go through it really quickly. And then comes, a little bit of front end. So until this point, you're pretty good at backend. If you've done all of this well, everything from point 1 to point 11, then you can build backends fairly well. I think one more thing I would add would be to write tests for your backend applications. And then you're a great backend developer. then you should probably move on to front end, because most probably a company that's hiring will hire a full stack engineer and not a pure backend engineer, and it's not very hard of a skill to learn. If you've been able to learn everything from point 1 to point 11, then point 12 is probably not that difficult. There's a little bit of a learning curve, but nothing crazy compared to backend. So finish off React and Tailwind, which probably can be good enough. Like that's when you're a full stack engineer. I'm skipping through a bunch of sub points here. The React, maybe you can do 10 different things and learn different things. Tailwind, probably not. Like Tailwind is fairly simple. But React is probably, again, 5 to 6 days or classes of an effort before you can actually say you're decent at React. There's a bunch of subtopics to understand well, which I'm not, noting down over here. Followed by Next, in case you want to learn it, you'll probably be fine without Next.js as well. But again, a lot of US-based startups just have Next.js as their stack, as in they don't even use Node.js or Express for their backend. They create their backend and their frontend both in Next. Hence, it is a decent stack to know of. A few other stacks to point out would be something like 𝗟𝗶H, the T3 stack, 𝗟𝗶H.js is a new framework now. There are like a lot of new startups will probably always move towards something fancy. And for good reasons. Like 𝗟𝗶H.js is a faster framework compared to Express, like significantly faster. Bun is significantly faster compared to Node in a bunch of benchmarks. And hence it sort of makes sense why startups are moving there. But if you're decent at Node.js, none of these are very hard to pick up. So if you're decent at React, Next.js isn't that hard to pick up unless you really want to, get into the nitty-gritties of how Next.js works and a few very Next.js specific points. Finally, if you do feel like learning other protocols other than HTTP, which is the most popular one, then WebSockets and WebRTC are two decent protocols to look at. There are a bunch of other protocols like XMTP, there is server-side events, there is Telnet, there is the SMTP protocol. None of them will probably be needed for an early engineer, and hence they're good to know, but probably not something you need to dive too deep into. WebSockets, you probably need to dive mildly deeper into, and WebRTC, again, I'd say not super necessary for a full stack engineer. And lastly, slightly more backend heavy concepts. Queues and pub subs are just two of them, but there are various ways backends can communicate. If you know these, you're probably sorted for 99% of the use cases, and this will just make you a little better at backend. This is not an exhaustive list. Now that I think about it, this is like a good list. This is like a good entry level engineer list. After this, you can probably explore everything. You can probably explore all this on your own as well. But basically, if you've done everything from 1 to 16 really well, that means you're pretty much good to go to learn anything in the MERN stack, or probably the JavaScript ecosystem is what I mean. This will get a little tricky if you move from JavaScript to Java, or JavaScript to Go, or JavaScript to Python. So there are a bunch of other challenges there to discuss. I'm not writing them down here. This is specifically for very simple basic MERN stack engineer. And if you need more topics, let me know in the comments, because I can think of 1,000 other things to add over here. But if you want a more actionable, to the point roadmap for full stack, I think this is it in terms of the syllabus. In terms of the projects, build a to-do app until the MERN stack point. I think everyone should do this. And if there are 100 people starting full stack, probably 90 would drop off until this point. So only 10, you're only left with 10 after this point. Who can create a to-do app, a course selling app, an e-commerce app. People tend to build this and just stop, which is where, if you do move forward from there, the probability of success is much higher. So just build this initially to learn a few things, and then I've put out a few here that I primarily feel like are good projects, in the sense they touch a lot of these technologies that we've talked about on the left. And also they're not very trivial, in the sense there is some level of something extra that's needed more than full stack. That's pretty much a simple answer there. Okay, the reason a lovable or a Codeworks or a trading app is slightly better than a to-do app is because they might require a protocol like WebSockets, which is point number 15, or something like Queues, which is point number 16, which you probably don't need in a to-do application. It's a simple one. Lovable will require hitting LLM APIs, parsing data from there. So it's a little out of the comfort zone. It's a little out of what's already been written on the left, which is why I think these are better projects compared to the ones mentioned, like simple projects like an e-commerce project, something like that. Here are a few resources. I think this channel covers a bunch of this. Primarily, if you'll find resources on one thing, it'll be on full stack on this channel. So it might be one good channel to look at. Angela has a course. It's a paid course, but it's pretty cheap. I think it's like 300 rupees on Udemy. Great for beginners. So if you feel like you need a lot of handholding initially, if you've never done coding, I think it's a decent resource. React.dev specifically for one thing, which is like the React website, but I haven't found a better documentation in the Node.js ecosystem compared to what's present here. So whenever you do reach React, I think React.dev is great. But again, it's probably great for people who don't require a lot of handholding. I read it fairly often, but maybe I wouldn't have been able to digest it when I started React back in 2019, I think. So just keep that in mind, and based on that, make a decision. And lastly, the best thing you can do, which again is less handholdy, is look at open source projects. I've written them down into two categories, which is GSOC organizations, which there are a lot of them in JavaScript or the JavaScript ecosystem generally. And then open source companies, which most of them are written in Next. So if you can read through their code bases, try to understand them, try to maybe solve an issue or two. And when I say solving an issue, I mean solving a substantial issue, an issue that actually provides value to the company, that is a good resource to actually learn something, because you're not just creating your own projects in your way, you're contributing to a project which is being used in production, which is probably 100 times better than creating something on your own, because there's no one to really ridicule you on your code if you're writing code yourself, compared to if there is some code that is written already being used in production and you're providing value there, which is why I feel point number 4 is super necessary, but there are a few cautions here. One, as a beginner, very hard to understand code bases. 2, I mean, it's probably easy to understand and solve an issue using GPT, but if you don't know the points on the left, it'll probably make your life very hard. And number 3, it's easy to spam open source orgs, but don't do that. It just creates, bad incentives for people to open source in the future. All right, with that, that's full stack. We'll move on to the second one now. I think post full stack, DevOps is the most obvious choice, because if it took you, let's say, 2 months to learn full stack, then it'll probably take you another 2 months if you really want to learn DevOps well. So let's do that next. Let's get into what you need to learn, the syllabus, the projects, and the resources for learning DevOps. All right, DevOps, the slightly harder bit, the really hard to get hired for bit as an early engineer, because a very critical bit for a company, and no one would want to hire a fresher over here. Most of the times you grow in a DevOps role is by joining a company as a full stack engineer, front-end engineer, back-end engineer, slowly taking a little bit of ownership, and then eventually owning more of the code base. Sorry, not the code base, the infrastructure. So basically, a caution, don't feel like you can get an entry-level job here. If you do get an entry-level job, it's mostly for extremely low-paying packages, because they hire you to train you for 6 months to a year before they actually give you something critical. The best thing you can do, join a company as a full stack engineer, and then over there grow as a DevOps engineer, and then you can of course move from one company to another. If you have some proof of work, there's a very big chicken and egg problem. No one is going to hire you as a DevOps engineer, which will lead to you not becoming a DevOps engineer. So the cycle sort of continues. So you can do a bunch of things, but you'll have to spend some money on a cloud environment, bringing up resources, bringing down resources. So make sure you have like $100 on the side to spend on AWS, GCP before you start this. We'll kick things off with the simplest one. This is something you should know generally, irrespective of if you're doing, DevOps or not. Even if you're doing full stack, you need to be fairly decent at the terminal, just understanding basic bash commands, nothing crazy, which includes, how do you explore various folders, files, create new folders, open a file, edit a file. If you want to really grind, then feel free to learn Vim, NeoVim, and make that your primary coding environment. But generally, if you understand most bash commands and are able to, push to a Git repo is a good litmus test. If a lot of people are not very comfortable with the Git CLI, it's a good litmus test of someone if they've worked in the terminal or not. So things like this, just make sure you're able to work through the terminal yourself without repeating a command. I think that would be great. So just go through probably less than a week. Just make sure you just stay in the terminal, try to spend a lot of time there, and by the end you should have enough muscle memory / will to be able to do things inside the terminal. Learn about VMs and bare metal machines. I think this is the point where things get slightly fascinating. Deploying your code and how does your code get deployed, and what are cloud environments, believe it or not. Cloud did not exist until 2008. So people used to actually rent racks in data centers themselves to be able to deploy their application. And now it's fairly abstracted from most humans like you and I. But understand the difference between a virtual machine and what a bare metal machine is. What happens if you actually go to a data center and rent a machine, compared to if you get a virtual machine from AWS, GCP, what are the performance upsides and downsides in both. But 99% of the times you're going to use a cloud environment, you're going to start a virtual machine over here. So as long as you understand what a VM is and how does it actually work under the hood, and what exactly is happening when you go to AWS and create an instance, you're good to go on this section. Process management plus reverse proxies. This is the most vanilla way to deploy an application, be it the front end or the back end. Process management basically means making sure if your process crashes, you're able to restart it automatically. Reverse proxies are a way for you to deploy multiple applications on the same server, which is something you probably want to do early. So a lot of early startups just have one server where they're running their front end, their back end, maybe 7 different backends, maybe even the database, which is like fairly dangerous. If a company is doing all of that, how can you join that company and understand their infrastructure? How have they deployed their application? Most probably using process management plus reverse proxies. One more thing, very common thing to know, is how to generate certificates. What are certificates? How do you move your website from HTTP to HTTPS? And up until this point, I would call the equivalent of this point of full stack. If you understand the MERN stack, by which I mean if you're able to create a MongoDB database and put some data in it, create a to-do CRUD application, you're a very basic full stack engineer. You basically are fascinated. It's like if I start to learn chess, if I know all the moves and some very basic, I'm able to beat someone who's rated 800. The equivalent here would be understanding everything until this point. The equivalent in DevOps would be everything until point 4. Point 5 onwards are a little more, call them industry ready things, / if a company has hit a certain scale, which not enough companies hit scale. Probably 1% of the companies actually have enough users to have a need to move from point 3 to point 5, which is scaling their infrastructure beyond a single machine. That means having multiple machines running. And there are many ways to do it. The most vanilla one is to either create an auto-scaling group in AWS or what are called managed instance groups in GCP. Every cloud has a different name for it. But it's basically a bunch of machines that you've started, all of them handling traffic in some sort of a round robin fashion, so that if you have millions of users hitting your servers, there's not a single virtual machine that's being hit in the end. There are multiple machines, and it's easy for you to scale up and scale down based on various criteria. Biggest of the companies, I have a friend who works at Zepto. They use the same thing. Zepto has hit scale, right? Like infinite scale, or what you'd expect from a very big startup. Yet they don't have extremely fancy infrastructure. They of course don't have point number 2, which is a single virtual machine. But they're also doing fairly well with auto scaling groups, managed instance groups. And the life is pretty sorted. They're able to handle that scale with a very simple AWS construct called auto scaling groups, which is why it's a great thing for you to know. At this point, you can join mid-size to a slightly large size startup that has hit scale and needs to serve more than 10,000 customers at the same time. Then come again slightly more not needed but important concepts. So when I say not needed, I mean a startup can probably run without containers. But if you are calling yourself a DevOps engineer, most probably the company that you're joining is going to use containers in some form or fashion. What are containers and container runtimes is one concept, which is a more Linux specific concept. And then what is Docker, which is a specific container runtime, is the second concept. Most of the times, 99% of the companies again would probably use Docker as their container runtime, even though there are many other alternatives now that are trying to compete with Docker. But most probably will use this. So spend some time understanding what container runtimes are, and then directly dive into Docker. Maybe a little bit about history of Docker, and then just move on to how can you start containers, start create images, push images, pull images, and so on and so forth. There are more advanced concepts here. Docker is one thing I would break into 3-4 subpoints. Which is basic Docker commands, writing a Docker file, multi-stage builds, orchestrating Docker. Docker has this feature, call it a feature, but an alternative to Kubernetes called Docker Swarm, which you can learn about, but no one uses Docker Swarm. Almost everyone uses Kubernetes in case they want a very fancy infrastructure with container orchestration. Container orchestration is a jargon that I'm using, but it basically means orchestrating or starting more than one containers at the same time. And Kubernetes is again one way to do it, but there are many orchestration frameworks, and Docker has its own, Docker Swarm. Kubernetes is another one. There are many others that let you start instances, or more technically containers, on thousands of virtual machines. Why does a company like Zepto not use this? Why do they use this? Depends on them. I think they have the reasons to. And again, as a startup, things get fairly complicated if you do move to a Kubernetes. There are a bunch of tweets about people trying to move their infrastructure to K8s or Kubernetes, and they're just moving it back because of how expensive it is to hire engineers, how expensive it is to debug something. If any node in a Kubernetes cluster goes down, the kind of expertise that is needed to manage a Kubernetes cluster is probably something you don't need, or any company or most companies don't need, which is why it's a great thing to know. But most probably if you join a company, you might be the one migrating the code base to Kubernetes or the deployments to Kubernetes. Most probably the company that you're hitting, if you randomly throw an arrow, the company is not using Kubernetes. Like a company like Razorpay does use Kubernetes, but a company like Zepto does not. So it really depends on, I guess, the time that the company has spent. I think when Razorpay started, they were not on Kubernetes. I remember when I was just starting out as an engineer, they were hiring for this specific role of, migrating their infra to Kubernetes. But you get the idea. Important concept. If you're a DevOps engineer, definitely something you should know. I've already broken it down to 2 parts, but probably, can be broken down into 10 different parts. Depending on the depth of Kubernetes that you want to go into. But if you just want to do the basics, I have a video on YouTube, and that is probably enough for you to be able to deploy everything that you need, or a full stack application or whatever you might need onto a Kubernetes cluster. All right, moving on to a very simple concept, CI/CD. Yeah, if you know how to write tests, you should probably be testing every PR on GitHub. If you are deploying an application, it probably makes sense to deploy it directly via GitHub rather than an engineer actually SSHing into a machine, downloading the code, restarting it. Fairly simple concept, should probably take you a day. Monitoring and observability is again a fairly vast concept. You can spend a lot of time here or null, depending on whether or not you want to add monitoring to your application. This is also borderline, more of a full stack challenge compared to a DevOps challenge. But a lot of times the DevOps team is what is looking at observability tools, which is why I've put this here. If you join a company and anything breaks, engineers are probably sleeping at their houses and they need to be woken up. That happens usually in an automated fashion, based on, if the request latency becomes really high, or if the number of failures are really high. All of this needs to be tracked automatically, and that broad concept is known as observability. There are many ways and tools to do it. Datadog is a very commonly used public company that probably is worth a lot of money. And then there are free alternatives like Grafana, Prometheus. There are many stacks that you can use to track your application, if it's performing well, if a release has broken something, if the performance is overall going up or overall going down, your net revenue, your net sales or net requests per second, failure requests, success requests, so on and so forth. Which region of the world are people hitting you? What is the time in which your application is alive? All of your logs from the last 3 months, let's say, all in a single place, so that the engineers can probably just look at those logs in a centralized dashboard compared to SSHing to various machines. Are one of many reasons you want monitoring in your application. Any mid-sized to big-sized company will probably have it. And again, a very niche sort of a skill for someone to know. Can be broken down into various categories. I've put it as one point here, but probably can go fairly deep based on what you're learning. Infrastructure as code, again, something 99% of the companies will not use, 1% will. And depending on a very specific use case, sometimes it sort of makes sense to be able to orchestrate nodes or move from one cloud environment to another, or just prepare for doomsday or disaster when you have to move, from one cloud account to another. If that happens, if you're migrating from one cloud to another, or if you're preparing for the day in which your DigitalOcean account just gets banned and you need to restart the resources as quickly as possible, it makes sense to have all of your code written in files, or all of your infrastructure written in the form of code. That is what IAC means. It makes it very easy for you to move across in a multi-cloud environment. There are many reasons this happens, or many cases in which you need it. I give one example. The example is if you a lot of times you need, this is a very niche use case or very specific use case, but I can still talk about it, which is a lot of times you need to build trustless systems, by which I mean your backend is deployed somewhere, but you can't really trust the engineer that's, migrating that or deploying that backend. So you might have 3 different AWS accounts and have 3 set of engineers who are very disjointed, they don't know each other, who have access to these 3 AWS accounts, and they can all use the same infrastructure as code files to start infrastructure in their respective AWS accounts without being able to talk to each other and without being able to clicking buttons in which a developer can make mistake. If there is some code that clearly defines what infrastructure needs to start in a specific AWS account, then if you give that code to 3 different engineers, all 3 of them can respectively deploy the same infrastructure in their AWS accounts, and by the end you have 3 different set of resources that are completely trustless, and not one engineer knows the other engineer. So if an engineer does want to attack your AWS account, the other 2 AWS accounts will take over. That's one specific use case where IAC makes a lot of sense, because it will be really hard to track what infrastructure needs to start across 3 different AWS accounts when the teams can't even talk to each other. But if they have the code, all they have to do is apply the code, and then the resources would start themselves. That is one specific use case where IAC makes sense. Point 8, 9, and 12 are very niche points that most companies would probably not need, would probably not use. And that is why it becomes really hard, even if you have that skill, most probably it's really hard to find that company that requires that skill. Even if you do reach that company that does require that skill, they'll probably, dismiss you as a very early engineer. That's the problem with DevOps generally. But as you get more deeper into these topics, the problem sort of persists. People who do have such niche use cases of deploying across 3 AWS accounts to build a trusted system will probably not hire someone who's very early. So keeping that in mind, it probably makes sense to, to figure out when to stop in this DevOps cycle, because it can just go very deep. And if your motivations are to get a job, a lot of times that depth is not going to translate to a job very quickly. It'll probably take years for you to have a lot of experiential learning, because before you can actually apply IAC to a company or change the IAC code of a company. All right, CDNs, object stores are pretty simple. Should take you less than a day. How should you deploy front ends? Where should you upload images, videos, things like these? Fairly simple concept and should take more than a day. Sandboxing and Firecracker is a new one. Firecracker, or generally sandboxing, is a slightly old concept, but highly abstracted from us engineers. Whenever you create a virtual machine on AWS, or if you've ever dealt with Lambda function on AWS, they run in what's called a sandbox. So if you've created a Cloudflare worker, same thing happens. Your code runs in a sandbox. And there's a lot you can do over here to be able to use basically a lot of infrastructure, a lot of machines to deploy 10,000 applications. So on, that hardware, those machines. I'm not explaining this really well, but basically if you think of Lambda functions or serverless functions as a problem statement, how would you let thousands of developers deploy not very small, very small is the wrong term, but how would you allow thousands of developers all around the world deploy a Lambda function or deploy a Cloudflare worker? A Cloudflare worker should scale up and down themselves, or a Lambda function or a serverless function. The scaling of the function depends on the infrastructure provider, which could be AWS or Cloudflare. Doing that is a little hard because you can't predict traffic. So either the AWS or whatever the cloud provider is that's giving you this serverless functionality, either they need to scale infrastructure using these constructs, ASGs, MIGs, or Kubernetes, or they can do something else, which is called sandboxing, which is where Firecracker was sort of born. Firecracker came out of AWS because that was the technology used for virtualization or creating small sandboxes in AWS for Lambda. Eventually, it is now being used in various use cases. If you use Lovable, look at any AI application, even Claude today. If you see a deployed version of your application, it's most probably in a sandbox somewhere. And hence, this use case became very popular in the last 6 months to a year when everyone needed sandboxes to run their AI code. Hence, this is a new sort of something that saw a lot of growth at the consumer level. But when I say consumer level, I mean developers like you and I had to deal with sandboxes now, or this thing called Firecracker now, because developers like you and I now need to deploy AI applications for end users. If you're building something like Lovable, you have to deploy AI code for your end users. You probably shouldn't do that, in a non-sandbox environment, which is why everyone is now creating sandboxes, and which is why companies like E2B are growing really quickly, because E2B is one new company which uses Firecracker to basically provide the same functionality Lambda did, but to end users like you and I. So if you're ever building Lovable, you'll probably see this in some form or fashion. And not just Lovable, this is one example. A lot of other companies, even in some concept of context engineering, which is how do you prompt an LLM and try to keep the context really small. Sandboxes are being used to be able to store a lot of the context on sandboxes when you're having a conversation. So whenever you're having a conversation on Claude, most probably there's a sandbox somewhere where a lot of your context is being cached temporarily while you're having the conversation to keep the final AI context small. So because of these use cases, sandboxing is very popular. Never really introduced this before, but first time I'm sharing this as a new thing to learn. Probably if you want to be a DevOps engineer. Moving to the projects. E2B, the technology that I talked about, which is a B2B company that lets you start sandboxes on demand. They're open source, so you can look at their code base. Their code is written in Go though, but it's fairly easy to read if you try to reach the right files. I've gone through it, which is why I'm saying it. Replit, again, is a company that would heavily depend on E2B, so it would require some level of sandboxing. E2B, if you use E2B as a black box, then Replit becomes fairly easy to build. If you don't, then again, you're basically building the same thing again. So point 1 and point 2 are fairly similar because the difficult thing in both of them is sandboxing. Even though in Replit, there's like a bunch of other challenges because there are 100 different frameworks you have to support or languages you have to support. And there, at least Replit uses concepts like Nix, if you've heard of it, which gives you reproducible builds, which basically means if you want to start a Node.js version with a bunch of dependencies in a predictable fashion, then the way to do it is using either Docker images or using something like Nix. So depends on the depth that you want to build this in. They have a bunch of open source resources sharing how Replit does it. And then Cloudflare Workers is probably in the same category. Honestly, all three of them are very sandbox heavy. I should probably put more projects here. But unfortunately, there's not much to build when it comes to DevOps. It's more to deploy. So you have a full stack application. How you deploy it? Do you use point number 3? Do you use point number 8 or 9? Do you use point number 5? That depends on you. So there's no real project to build other than, B2B DevOps companies, something like E2B or Replit that, has B2B DevOps challenges. Resources, I don't have many. Unfortunately, DevOps, again, is a very exploratory and experiential field. So keep that in mind if you do want to dive into it. The ones that I have put out both blogs of 2 sandboxing companies today, Modal and E2B, both do the same thing. And both have blogs that will probably teach you about this new technology. Everything else, a lot is present on the internet for you to learn. So you'll probably have to, explore those resources yourself. With that, we'll move on to the third one, which would be, let's do AI next. What would be a roadmap for a good AI engineer? Let's get into that next. All right, this roadmap was built with the help of a friend who currently works in an AI company. He's fairly young, but is in the borderline category of AI researcher and a applied AI engineer right now. It's a fairly decent roadmap to understand how can you probably get a little bit into research, because it does cover some of those topics, but mostly around applied machine learning, which means, basically means building agents. but at the same time, it does answer a bunch of questions in case you do want to get into the history or understand how LLMs work under the hood. Kick things off with the history of AI, by which I mean how did we even end up at transformers and how were things done before transformer, the architecture came out. A lot of researchers were trying a lot of things, and then transformers, the specific architecture, ended up eating everything else. So what were those things? And how did we finally arrive at an architecture that's probably the best today for not just language tasks, but also for image tasks, video tasks. Everything is today being done through transformers. What came before that? The answer is deep learning and a bunch of mathematical jargon, which are terms like sigmoid functions, if you've heard of them, or backpropagation, the standard algorithms that you would use to create neural networks. So if you've ever created neural nets before, if you've done a little bit of deep learning back in college, standard classical machine learning, classify if something is a cat or a dog sort of questions, or the very standard MNIST dataset problem of identifying a digit. If you've done those, that's probably what you need to cover if you haven't done those, which is how classical machine learning was trying to solve the same problems that transformers are solving today. Then comes a very important concept in the sense, even though it was used in classical machine learning, it's also used today, which is neural networks. And PyTorch, probably the most popular language you want to code neural networks in. You can code a neural network, it's just a graph in any language that you want. But most probably you want to use a framework like PyTorch to do it because it makes things very easy. It's highly optimized. Most of it, is boils down to commands in C that you can actually run on, hardware if you want to, and hence makes the developer's life easy. And most probably you can squeeze the maximum performance from your neural network if you're using a framework that's highly optimized to do mathematics, matrix multiplication, whatever, rather than writing it yourself. PyTorch is fairly vast. It depends on, again, the depth of it. How much of it do you want to learn? Probably makes sense to learn it on the go as you're building a very basic neural network. Learn the very first things, and then eventually, as you build probably a transformer yourself, is when you'll learn more functions that PyTorch exposes to you. A few extra classes that I've written over here is again things that used to happen before. Attention was a thing that includes recurrent neural networks, long short-term memory, and sequential models. All of these for in case you wanted to do language tasks, which could be completing a sentence like ChatGPT does today, or translation. And then I've written another one called CNNs, which is convolutional neural networks. Again, all of this is like pre-2018. I did this back in college. It was like 2015, 2016. So none of this is new. None of this is needed either. So it really depends on if you really want to spend your time here. You can directly dive into attention, or you can go a little bit into the history and probably spend, a month understanding how CNNs were trying to target object detection or image, or how diffusion was done back then for image generation. Or you can directly dive into attention and take everything before that as a black box. But a lot of these things mentioned over here are outdated architectures compared to attention, and attention doesn't really, probably inspires few things from these architectures, but doesn't really use any of these under the hood. Then comes probably, which can be the starting point of your learning journey, would be coding simple attention and going through the attention paper. The attention paper originally was not built for what we do or use it for today, which is having a conversation and asking questions, getting answers. It was primarily meant for translation. Eventually the architecture was so good that now it's used in not just language tasks but image tasks as well. But back then it was created as a translation paper. How can you translate English to Spanish? And attention was a decent architecture to do it. So going through that paper, probably just the important parts and trying to code attention is step one. And then diving into a lot of ways it has evolved over time. Every company has its own architecture of coding an LLM today. Some of them open source, some of them not open source. But how do you move from that, the original attention paper, to what ChatGPT is today, which is a user assistant model where you can ask an assistant to do a bunch of tasks and the assistant will do it for you. This section is primarily on how attention is done today by various companies, and what are they're all basically trying to optimize for memory and compute. How quickly can you train a model? How cheaply can you train a model? And how cheaply and quickly can you answer a query? So now people are trying to optimize the attention architecture more and more. This includes things like KV cache, grouped query attention, multi-thread attention. And this is a new one that I think DeepSeek released today. I think it's I forgot the full form. This came out last week. Point 5 is around how the transformer architecture has evolved over time. In the end, everyone is trying to optimize for compute, memory, and speed. How can you train a model really fast? How can you train it in a fairly cheaper fashion? And how can the model answer queries as quickly as possible? And of course, the quality of the final response matters as well. To achieve this, attention architecture slowly introduced more and more optimizations. So Transformer has gone through a bunch of standard optimizations that you might have heard of, like KV cache, or more nuanced and new ones. For example, I think DSA is the one that came out from DeepSeek very recently. and everyone's sort of, trying to optimize the attention architecture of the transformer more and more to achieve not just better quality, but also, better inference times and consume less memory, so on and so forth. So what are the various variations of transformers that you can build? How do they apply to the very specific task of, an assistant answering a user? This can go really broad if you want to, let's say, apply attention to images or other tasks. But specifically for NLP tasks, the goal over here should be to build a better and better transformer and use some data set, train the model on it, and see how the optimizations help in terms of the training time, the inference time, so on and so forth. Probably up until this point, you should understand what Hugging Face is and what it is used for. It's touted to be, the alternate of GitHub, which is sort of true, sort of vague. But basically, it's a place where people do deploy a bunch of their models, data sets, and a bunch of other things. Like they've basically done a lot of things in the same interface. GitHub is very specific. For example, it doesn't let you deploy websites. Even though it does, but like it's not out there on the website on GitHub. It has a very specific use case. Versus Hugging Face has, a bunch of tabs, including something like, Hugging Spaces that let you basically deploy websites or applications to, test on top of an LLM. So it's a more jargony sort of an interface, but in the end, it's a place where, people are hosting their models, hosting their data sets, hosting spaces to, showcase to the world, basically an open source version of, a lot of times open source, a lot of times just the model, the final weights of the model that you can use on your own machine and, pull the model to your machine and run it from there. So understanding how you can interact with the Hugging Face GUI and how can you use, a bunch of Hugging Face libraries to import models to your Python code and, run inference on top of the models that are hosted on Hugging Face. From here, most points until point number 13 are more applied AI, which again, more of the field where it's easy for an early engineer to get in. I think everything we've talked about until this point is one, a lot of history, and two, a lot of detail around the attention architecture, which is something that can be asked in an interview. I know a guy who just got asked, probably not too much, but again, deeper and deeper questions into how attention works and how can you optimize attention. Everything from point 7 to point 13 is going to cover more application layer things that a bunch of these LLM providers have provided to us to build on top of them. The simplest one, and a very common sort of thing you might have heard of would be vector databases and RAG, which primarily are used for search. If you have a lot of data that you need to search through to be able to give as context to a prompt, which is the most common use case of, vector databases and RAG. Then comes, a vector database, which basically stores a bunch of text in the form of vectors. And if there is some new text that needs to be compared to the existing text, if you want to search on top of the existing text, is where you can use vector databases. It is one of many ways to retrieve text, but there are other ways. For example, for coding tasks, vector databases and RAG is not the best way to search for something specific. If you want to search for a specific thing in a code base, vector databases are probably not the way to go. A simple grep might be, a better way to search through a code base to find something specific. So it depends on the task. For essays, it probably makes sense because vector databases, or these vectors carry some context, and you can search through, let's say Harry Potter novel around, I don't know, Hagrid, and it'll give you all the places where Hagrid was mentioned, or Hagrid was somewhere in the context, or there is some level of Hagrid in that specific statement, compared to a coding task where if you're trying to search for an endpoint where a to-do is being created, it's easier for you to grep through the code base and retrieve it compared to use vector databases. So a very specific thing to learn for specific use cases, but not the only way to retrieve data. The reason I say that is because it's overused right now, I feel, on a bunch of use cases where it doesn't make sense. Context engineering, this one is an important, long, and a very novel sort of a statement. Now, context engineering was really a thing, like prompt engineering was a thing. Context engineering is something new. It basically means figuring out what's the best context you can send to the LLM for a specific task. And if there is a lot of back and forth happening between the human and the LLM, how can you keep trimming, summarizing, breaking the context, and what are the various approaches to do this, to be able to keep your prompt as, simple and most to the point as possible, because one, you have token limits. You can't, let's say, send more than 1 lakh tokens. But two, even if you do tend to hit 30% of the limits, you'll start to see the model hallucinate or forget data that's before. So it makes sense for you to keep trimming data. What are the various approaches to trim this data? As I said, all of this is very exploratory at the moment, and every company is sort of figuring this out on the go. How can you make an LLM really good at longer tasks or more difficult tasks? Context engineering is one way to do it. How you do it depends on the very specific use case. For a coding task, it would be very different from a deep research task. A deep research task's goal is to research on a very specific topic in the deepest fashion. A coding task, a very difficult coding task might be to, solve a specific bug in a repo. For both of these, it makes sense to do some level of context engineering rather than just, sending the whole thing to the LLM. How do you do that? How do you summarize? How do you evaluate if the way that you're doing summarization is good or bad? Is you should spend your time on here. Very exploratory at the moment for, even companies that are trying to build this. Everyone is, figuring this out as of today, as they're, trying to target their applications to do more difficult tasks. If there's a lovable competitor today that's saying you will build a very elegant and end-to-end full stack application for you that just replaces your business, they'll have to spend a lot of time here trying to figure out how can you do such a massive task in a single prompt. With that, agents, which is a slightly overused term, which it basically means, talking to an LLM and giving the LLM access to some what are technically called tools. So maybe before agents, understanding what are tools, and then how can you build an agent on top of a tool. Agents from first principles, which basically means, without any agent framework, how can you build an agent and what exactly is an agent and how is it any different from, a chat interface from which you're talking to an LLM. Then probably using an agent framework. There are many now, Crew AI, LangChain, LangGraph, figuring out what exactly they're doing. And how they make your life a little easy when trying to build an agent. Specifically, if you're trying to create multiple agents that need to talk to each other, and one agent needs to depend on the response of another agent, and one agent needs to be able to call another agent using a library rather than building everything from scratch. Even though building a lot of this from scratch isn't that difficult, and a lot of companies today tend to build their agent frameworks in house rather than depending on an agent framework, because a lot of these agent frameworks are moving very quickly and changing the way you need to write code using them. Like LangChain and LangGraph is a good example of this. So the original repository was LangChain, and then eventually they realized graphs make more sense, so they moved on to LangGraphs. And a lot of times there's not enough backward compatibility in these frameworks, and hence there's not enough that they provide for you to be able to depend on them. But at the same time, you should know how to use one agent framework to build an agent. Memory, which is again a very specific concept in terms of the use case. For some use cases, long-term memory, vector databases make sense. The most common way to do memory is vector databases today. So if you have an application that uses AI, let's take a decent example of, an image repository, or let's say text repository, a place where you're just dumping text or dumping blogs, and then you need to be able to search on top of them. It would make sense for you to use some sort of memory and most probably vector databases. You can do this using, an open source vector database that's hosted, a proprietary vector database that you have to use in a managed fashion, or using one of many libraries that exist today, like if you've heard of M0 or Supermemory, which are trying to tackle this specific problem of memory, and making it easier for developers to be able to interact with these memory backends or memory databases. Most of them being vector databases. You can go very deep into this depending on the level of the application. For example, for Cursor, they heavily index your application, so it sort of makes sense. For Lovable, it's a very small application that you're building, so most probably context engineering is all that you need to be able to build something like Lovable. To build something like Cursor, where you need extremely fast responses in terms of the tab response that you need to see, extremely big code bases, it makes sense to index the code base. So figuring out when you need it, and if you do need it, do you use library natively? How do you chunk the responses that go into vector database? That's probably more of a vector database question than a memory question. But basically, point 8 and point 12 would probably go a lot hand in hand, because most common way to do memory right now is using vector databases. MCP, again, a very new thing, very close to tool calling. So if you understand tool calls, it's probably very easy. I have a video on it that covers it as well. But long story short, a way for LLMs to call not a tool on the backend that invoked the LLM, but to call some sort of a remote tool, basically allowing an LLM to be able to interact with the 𝗟𝗶ः API is the example that I took in my video. But very fancy thing that came out. I don't know how adopted this is at the moment, but any chat interface that you go to, if you go to Claude, they do let you, link your Google Drive or your Gmail account through MCPs so that your LLM can interact with your Google Drive to help you retrieve images, or to your Gmail to, help you reply on images or summarize an email, so on and so forth. With that, a few other deeper non-applied AI topics. I wouldn't call these research topics either. Like, they're much simpler compared to the attention architecture that we're covering, from basically point 5 and point 4. But at the same time, slightly more nuanced use cases that only a few companies would need. Computer use is the first one, which, as the name suggests, is how do you allow an LLM to be able to control your machine? And the answer pretty much is what you are is in the direction that you're thinking in, which is you take a screenshot, you forward it to the LLM, and the LLM tells you where to click, and then you click, and then you forward another screenshot, so on and so forth. Here you can do a bunch of things. You can take a screenshot, or you can take the HTML of a website and forward it to the LLM, so the LLM can tell you where to click. But to be able to allow the LLM to be able to use your machine, you have to give the LLM not just text, but maybe an image, maybe video, maybe some HTML, like we talked about. And this is where multimodal agents come into the picture, which means a model which can not just take text as an input, but also an image as an input. As easy as that sounds, to be able to have an image along with the text, we do that on ChatGPT fairly often. The math that goes behind it is pretty heavy, because there's a specific architecture that attention uses to be able to generate more text from text. It's a very simple problem. It's not a simple problem statement, but it's a more defined problem statement compared to an image, which is very hard to define as text. So how does that happen? How does an LLM take not just an image, but let's say not just text, but maybe an image, a PDF, a video as an input, and is able to gather context on what's happening in the image. Fine tuning. What is fine tuning is one topic, which is understanding what are weights. If you understand the attention architecture well, what are the final set of weights that come, and how do you eventually fine tune your model for specific use cases. If you look at any AI lab, they create various variations of their models. There is probably a normal model, there's a smaller model, bigger model, bigger model. There are coding specific models that come out with every release. So in the end, after the basic model is trained, there is various levels of fine tuning that happens where the model gets trained on what it eventually needs to do. Does it need to solve a user assistant sort of a textual task? Does it need to solve a coding task? Or does it need to do, I don't know, whatever use case you can think of? You might create like a JE specific LLM that's just primarily trained on JE data. Why would you want to do this? It'll have better responses. You'll be able to serve your customers better. You can also just train an LLM that's only trained on JE data, nothing else. That way, your response times are much faster, because the LLM doesn't really know 100 different things that it doesn't need to know. It only knows enough to be able to answer JE questions and nothing else. This is where fine tuning becomes important. One, providing better responses. Two, creating smaller models, like a small language model that is trained on a specific use case and is not really solving things that it doesn't need to, doesn't really know things that it doesn't need to. Then fine tuning can be done various ways. One is using data, and then RL fine tuning, which is a more popular concept that specifically became super popular after DeepSeek through, if you've heard of the term RHFL, I think RLHF, reinforcement learning using human feedback, which basically is training your model by giving it some sort of a reward if it answers things well, and giving it some sort of a penalization if it doesn't answer things well. Doing this gets very tricky. For example, if you want to train your model to be better at math, then you will ask it a question, it will give you an answer, and it's very easy for you to tell a math answer is a simple number. So that's easy to do. Giving it some points if it answers the right things. If it answers the wrong thing, then give it negative points. If it answers somewhere close, then give it slightly positive points, so on and so forth. This gets tricky on tasks like coding tasks. How do you train a model that's really good at, let's say, Node.js? You'll ask it a Node.js question, it'll answer a Node.js answer. How do you evaluate that answer? There are various approaches. You can evaluate using another LLM, which is one approach. Or you can create, specific coding environments in which there is something that's able to evaluate the response. For example, if the question that's asked is a comparative examining question, then the response can easily be tested using test cases, just like Codeforces or LeetCode does it. That's one way to create an environment, but this gets more and more tricky based on the specific use cases that you're fine tuning on. But it's also a better architecture for sure to fine tune. In the end, the final response that you'll get, if you have enough data and enough agents and enough environments to be able to train the model, is better than if you train the model using data that's already present. So fine tuning. How do you fine tune using data? How do you fine tune using environments and reinforcement learning? Evals, writing a bunch of, call them tests or, metrics or benchmarks to see if the LLM that you've trained, is it any better than the LLM before? If you start off with, let's say some version of any open source model, let's say DeepSeek, and fine tune it on a lot of Rust data, then writing actual tests, which are more technically called evals, that actually tests, is it any better? Is the new model trained on Rust code with reinforcement learning any better than the one that's not? So on and so forth. So writing a bunch of these and making sure the final output that you get, you're able to quantify it very easily if fine tuning worked or not, or if one model is better than the other or not. And maybe going through some open source evals and benchmarks that a lot of these LLM companies optimize for. Advanced topics, there's no end to this. Put 19 and 20 together, which is all that we've discussed right now is just text, which thankfully is most of the, probably 90% of the use case of LLM right now. But it's not limited, and LLM isn't limited to just text. Voice is the most obvious next use case. How are voice agents created? Not just, you talking to a chat interface through voice, but things like 11 Labs. How is voice actually generated, music actually generated through AI? Same with video, same with images. There's no end to how much you can learn from here, or a specific niche in case you want to dive deeper into it. But all of them boil down to attention now. All of them use some variation of attention to be able to do whatever projects. Agent framework is the most obvious one and probably the simplest one. Creating something like LangGraph that lets you create agents, sub-agents, lets the agents talk to each other, maybe add some memory on top of it. Why? It just gives you an idea of what, the overused term of an agent means, and what does it even mean to, create an agents framework? Because in the end, it's just a bunch of LLM calls and a bunch of things people have figured out in the last 2 years. It probably makes sense to, do LLM calls separately. So let's call them 2 agents. And then maybe one LLM call depends on another LLM call. So let's just call that a sub-agent, things like these. So a lot of fancy concepts, but in the end, very simple constructs if you're trying to build something like this. RL fine-tuning project press writing evals for it. This one's really good. Pick any problem statement. Let's say a JE, verifier, or a JE fine-tuned model, or a Rust fine-tuned model, or a React fine-tuned model. Try to find some data set on it. Try to train it on the data set and see if it's any better. Write evals for it. And then think of how can you create an RL training environment. How can you get a data set in which the LLM responds and you actually give it points based on, if it was a good response or a bad response, and how do you actually quantify the response? Can it be done deterministically through tests if you're doing something like training on math data, or training on Rust, or training on competitive programming? Or can it not be done deterministically for, tasks like, writing an essay? How do you create an agent or an environment for testing if the response is good for an essay, and how is it any different from, doing it for competitive programming? Devin, which is primarily a DevOps application, I would say. It does involve context engineering, but I don't think Devin does any level of indexing the code base or memory yet. I could be wrong. So if you do remove that, it's a very simple problem to build, and primarily a DevOps challenge of, when an issue is assigned to Devin, where does the sandbox start? How does it start? How does the LLM talk to the sandbox? How does the sandbox, after everything is done, deploy the thing to GitHub? Lastly, memory frameworks, which again, Mem0 was a good example of, an open source memory framework. It's just an orchestration layer on top of a bunch of memory backends. You can use one of many vector databases to, store your data. A layer in front of that that lets you, choose which backend to use, which memory backend to use, which vector database to use, maybe store things in memory, so on and so forth. Basically would again give you an idea of how memory is an overused or overly glamorized term, but under the hood, it's just vector databases, very close to, the first point here, which is that agents is just an overused and overly complicated term, which under the hood is just, a bunch of LLM calls. Cool. Resources. There are many over here. Most of them are blogs by various companies, for example, Cognition, Anthropic, LangChain. 𝗟𝗶H 𝗟𝗶H has a YouTube channel, which is a little hard to understand. I think he has a lot of videos, 5-6 hour videos of coding a transformer from scratch and explaining the architecture a bit. A little hard to digest, but if you can go through them, then probably the best way to learn attention, as quickly as possible. Then there is Coursera, which is, I've primarily used it for classical machine learning back in the day for, things like deep learning and CNNs. I think it's still free. I could be wrong, but I'm unsure if they probably do have new courses on attention. I'm unsure if they're paid or not paid. And then lastly, 3Blue1Brown has very simple and nice follow along videos on the architecture of a transformer. So if you do feel like you're more of a visual learner, then I think this is a great channel to go through to just break down the attention paper in a more visual 3D format. And I think he has like 6-7 videos explaining, the initial architecture and better architecture and optimizations, things like these. So if you do feel like you're a visual learner and you do want to learn attention, 3Blue1Brown and 𝗟𝗶H's channel are more around, research and understanding transformers. Everything else is probably going to be, things built on top of LLMs. And, everything has been figured out in the last 1 year, 2 year, as people have started to build these agent applications. What are the new architectures that they've learned in terms of memory, context engineering, and, how it can be applied. Cool. That's AI. Move on to the fourth section next, which is Web3. Pretty big shift. Honestly, just pick one. If you do think of, picking of one of two fascinating fields, AI and Web3, just pick one because both of them require a lot of great time and energy to go through. The last one, Web3, its roadmap, projects, and resources. Web3 starts off with intro to blockchains. That's primarily, why were they introduced? What exactly is a blockchain? What purpose does it solve? Basically going through a bunch of videos very honestly rather than text, trying to understand Byzantine fault tolerance, or distributed systems a bit, or just understanding why can't you do Bitcoin without miners? Why does everyone all around the world need to start these miners and validators to run a blockchain rather than it just being a single machine like HDFC Bank has it? Then moving on to some cryptography, which is what makes point one possible, because mostly blockchains are cryptography, not in terms of the private keys that we hold, but also a bunch of communications that happen amongst the validators. And specifically in case of Bitcoin, the validation, the way it is done through a bunch of cryptography. So primarily up until point two, I would still spend my time on Bitcoin, understanding why it was introduced, because everything else is just a variation on top of Bitcoin, and everything else is solving the same use case, which is creating a decentralized currency. That's what Bitcoin did. The other blockchains do 10 different things on top. But if you understand Bitcoin, then it slightly becomes easy to understand these more complicated architectures. Think of it like the initial attention architecture and then optimizations on top of it, or variations on top of it. So Bitcoin, initial architecture, and then Ethereum, Solana, ever other blockchain you can think of. More variations on top of the same base problem of decentralized money or decentralized code execution. Understanding the architecture of Solana is probably a lot of videos if you want to go through the white paper and understand ekdam in depth how does a validator run and what all processes are running inside a validator and how do the validators communicate with each other, how is consensus reached, or you can learn it from slightly high level, understanding what are blocks, what are slots, how are transactions packed together, how is the leader decided, how is it decided what validator validates a specific transaction, so on and so forth. So you should decide how interesting it is and how you're losing interest on point number 3. And if you feel like you're losing interest very quickly by going through the white paper, skip the white paper for now. You can always come back to it. The Bitcoin white paper you should definitely read. The Solana white paper depends on if you're able to digest it or not. Then comes Solana jargons. I've mentioned 2 of these, authority and owner, but there are like probably 30 different jargons to go through. Program accounts, system account, system program, authority, owner are 2. Probably there are many more that I can't think of right now, but I can go through the docs and quickly find. What else is a good jargon? PDS is another good jargon, but I've just mentioned that as a specific, a different point, because it's really hard to digest what program-derived addresses are, why are they needed, and it takes a few iterations to understand it. So think of them as, 2 set of things you need to learn. A bunch of jargon, jo shuru mein you'll understand the statements. What is authority, what is an owner? But eventually it'll make sense when you reach, smart contracts and executions and start writing smart contracts. But spend some time here so that eventually you don't get overwhelmed when you're writing contracts, writing front ends, doing things like these. A bunch of Solana jargon, PDAs, and then probably the simplest part of this whole architecture, which is going to be going through client-side Solana libraries. Solana/web3.js is the OG one. Now there are new libraries that are coming that are trying to replace it. But basically is a library that lets you interact with the Solana blockchain. So if you want to, at a very high level, just interact with the Solana blockchain and check how much Solana does Kirat hold, then you can use this library, call a simple function, get balance, pass in my public key, and you'll get the balance of Solana that I hold, or the balance of USDC that I hold, so on and so forth. So another library I would like to add over here would be @Solana/SPL token, which lets you get someone's token balance. What is a token? USDC, USDT, Trump, Bonk, Beam coins. A bunch of these are tokens on the Solana blockchain. So if you do want to get my Solana balance, you'll get it using @Solana/web3.js. If you do want to get my USDC balance, then you'll have to use a different library called @Solana/SPL token. You don't need these libraries. They just provide you extremely high-level functions to be able to gather information like this. You can gather this information without using these libraries as well. If you do not use these libraries, though, you have to basically decode a lot of bytes into numbers, into textual data, which gets really hard. And they abstract all of this from you, which is why people tend to use these libraries rather than interacting with the blockchain themselves. The data model on Solana, it's very close. If you understand PDS, you'll understand the data model. But basically, Solana is very different from how Ethereum is. If you're learning Ethereum, your life would be much simpler because the language that is used to write smart contracts there, Solidity, because of how data is stored on the Ethereum blockchain. On Solana, things are a little tricky, and kudos to the founders, initial people who've thought of this architecture. Because it's pretty elegant in terms of what the data model in Solana is. At the same time, it's very confusing. It takes, a few iterations to be able to understand it. Once you get it, there is a light bulb moment and you totally understand why it was made, the way it was made. But the data model and PDAs go hand in hand. So point 5 and point 8, make sure you do understand them before you move on to the token program. There's no way you understand the token program if you don't understand what PDAs are. The token program is the very first smart contract that you should look at. After you're able to interact with the blockchain, after you're able to send some money, you're able to create a wallet application. Basically, if you can create a wallet of your own, is when you need to now start to dive deeper into more complicated programs. Token program is one such program. It's very vast in terms of what it does, how it does it, and the kind of jargon you need. Basically, yeah, a lot of filtration happens at this point because a lot of people are not able to digest how the token program is written and what it does. To keep that in mind, if when you reach this point, and only if you are comfortable with the token program is when you should move to the next section, which is DeFi or decentralized finance, or how can you swap one token for another. It's the simplest problem statement to solve over here. There are various, call them architectures, call them approaches to allow people to swap money in a decentralized fashion. The most oldest one is AMMs, or automated market makers, and then the list is never ending. People now have now we have something called prop AMMs, which is the most recent optimal way to swap one token for another. But the more OG ones and more ones that are available, you'll find source code for them somewhere, are AMMs, DLMMs, CLMMs, and I wouldn't put perps in this category. Honestly, I would put AMMs, JLMMs, and CLMMs in one category, and perps probably is a very separate topic because it's very different from what the first three do. The first three let you swap one token for another. The fourth one just lets you speculate on the price of a token, so it's a little different from the first three. Probably break this down to 2 points. Probably don't learn about perps until a long time, especially if you're trying to code them. A little hard to code compared to the first three. Rust easy, Rust advanced. That's something that's good to know generally. I think if you want to be a distributed system engineer or want to join a company where Rust is being used, you will have to spend your time learning not just the syntax but 10 different things that happen in Rust. I have 2 videos that you can go through if you want to understand them. There's another very good resource called the Rust book that you can go through. But it's not easy to write Rust because of just how the language is written. The reason it's written that way is to provide a bunch of safety guarantees to you when it comes to memory. Right, my camera died, so I'm just going to move to my webcam for the rest of the video. We were here on Rust. After you're done with the Rust, you should probably learn about Anchor. It's a framework in Solana that lets you build smart contracts easily. Probably one thing you should do before this is write native contracts. After you've written native contracts in Solana, which was the original way to write contracts in Rust, you can learn about this framework called Anchor that makes your life a little bit easy. Then you can probably start to write some basic, what might be asked in an interview kind of contracts. Staking and escrow are the more popular ones. You can write them in raw Solana. You can write them natively. You can write them using Anchor. You can write them in a third framework called Pinocchio. Probably do all three. And one thing I would probably urge at this point is to create clients and tests for this, which is written here eventually. A client basically means writing some high-level functions in JavaScript, TypeScript, Python to call that specific smart contract function. Tests, as the name suggests, writing tests for it, which could be directly in Rust or in TypeScript. Then comes indexing, which is a sort of an underrated topic, by which I mean it's something that most companies need. A lot of companies would depend on third parties to be able to index the Solana blockchain. What indexing means is reading every transaction maybe that's happening on the Solana blockchain, or specific transactions that solve something specific. For example, you might want to index all the swaps that are happening on a specific DEX, or you might want to index every new token that is being created on the Solana blockchain. Things like these. How do you do it in-house? How do you do it by depending on someone else? MPCs and 𝗟𝗶හිrs, which are more private key specific concepts. In case you do feel like holding your end users' private keys. How can you do it? How can you do it in a more secure fashion? And how can you try to get rid of as many vulnerabilities as possible in case you do want to hold your end users' private keys? Generally not the great idea, but for some specific use cases it makes sense. A good use case might be something like 𝗟𝗶හි𝗸𝘀, which basically lets end users or other platforms onboard users using their Google account or their phone number. So if you do want to allow your end users to not understand or know the concept of private keys, but just want to let them log in via Google, is where you need to understand what MPCs are or what 𝗟𝗻𝗎 secrets are and how can you hold the end user's private key for them. Ad hoc Web2 plus Web3 and partially centralized contracts are pretty close knit, by which I mean a lot of times, a lot of applications that you interact with on the blockchain are not completely decentralized. I think the recent Camino versus Jupiter feud had some points around Jupiter's lending protocol not being completely decentralized. And a lot of times it sort of makes sense for a few applications not to be completely decentralized, but to be partially centralized. Why? Mostly, the answer is speed or, compute limits or storage limits on Solana. So one, it's not possible to do it. Two, it just makes it faster to be off chain. And hence there's a combination of a centralized and a decentralized contract that you might have to create. So how do you create those? And what specific use cases do you need them for? And how does the centralized backend in that case talk to the blockchain? And if your end user does interact with your contract, how does the centralized layer actually know about it and execute the final thing that needs to be executed? Cool. The projects I've written many. DEX and SEX are the popular ones. So centralized exchange is probably been the same for many years now. I think the New York Stock Exchange, whatever architecture they have, just use the same. That's probably what every centralized exchange is using right now. DEX architectures keep on changing over time. AMM is the oldest one. Then there was CLMMs, DLMMs. You can go to DLMM. I think that's pretty good right now, even though now they are not newer architectures, but at least newer competitors in this niche. If you've heard of prop AMMs, how do they work? I think is a very unknown challenge at the moment. And what is there a specific architecture they're using or something else to be able to trade so efficiently on chain is something we'll probably know in the next 6 months. But right now, DLMM is probably the gold standard of a DEX that you can create right now. A wallet is a more simpler application, probably something to do at this point so that you're okay or decent at client side Solana. Prediction market is a new thing to introduce because a prediction market they just became popular right now. Calci and Poly Market made them super popular, and they're much simpler to code compared to a DEX, and they're competing with DEXs in terms of daily volumes, which is why I think a prediction market, at least right now, is a decent project to build. It'll also give you a decent idea of how you can build on-chain order books, which is something that was done on DEXs but never really took off. But probably something that will take off or works well in production for prediction markets. Lastly, front ends. I've already talked about this, but whatever contracts you're writing, which there are some simpler ones over here, more complicated ones over here, writing clients for them, tests for them, or front ends for them. A few resources. This is a very comprehensive resource. It's very vast. It also covers a lot of topics that you may or may not need. Hence, steer with caution, but it's a great resource if you want to learn blockchains very comprehensively. And let's say you have 1.5 years, then a great curriculum to go through. The Bitcoin white paper is something everyone should go through once in their life. And if you do want to learn Rust, this is where I tend to learn it from, which is another YouTuber called John. But his videos are a little too technical. So just pick and choose if you want to go to this channel or something else. Specifically for Rust, nothing related to Solana over here. That covers Web3, which pretty much means it covers everything we had to cover in this video. This video was a roadmap on 4 niches. Hopefully you have some insights on what is needed to build in these 4 niches. I would still say start with full stack if you're very early. If you are already a decent size engineer, you have a job, you've been working in the industry for a year or two, or if you're really smart and early, then feel free to pick AI, Web3, whatever niche you want. And lastly, this syllabus was a small tease of what we've been trying to build up for the next cohort at 100x School. So if you do feel like you want to join this and learn all of this with a community for a fairly cheap price, I think it'll be like 4,000-5,000 rupees this time, then feel free to join the cohort whenever it comes. If it does come, it'll probably come in the next 10 days or so. If that does happen, I'll see you in the cohort. If not, there are resources, free resources, topics, everything out there. So do spend your time and learn these resources yourself. And hopefully it was an insightful roadmap for all 4 of these for you. With that, we'll end it. I'll see you guys in the next one.